In this lecture, we're going to go over some of the basics of downstream recovery. So you'll hear different terms for downstream, downstream DS, downstream recovery, DSR, downstream processing or downstream purification, DSP. They're all pretty much equivalent. And downstream recovery usually starts with the fermentation, what comes out of the fermenter. So with the fermentation ends, downstream recovery begins. And what comes out of the fermenter is whole broth. So this is spent media and cells. And the first thing that you do is cell removal or primary separations. And this is almost always based off of size. So the specifics depend on where your product is. So for example, if your product is the cells, then you remove the broth and you keep the cells, and that is your product. If the product is inside the cells, which would be most proteins, you have one different path. Then if the product is outside the cells, another path, right? So in either case, the primary cell removal is basically a size separation, and primarily is a result of filtration, microfiltration, or centrifugation. Obviously, if you filter or centrifuge and your cells are the product, you get rid of the broth and you keep the product. If your product is inside the cells, similarly, you would keep a concentrated cell suspension. And if the product is outside the cells, then you would dispose of the cells after the size separation and keep the cell-free liquor or broth, which would be another name for the clarified broth or the cell-removed broth. If the concentrated cell suspension is the path you're taking, then you would have to go through a cell disruption, and that's primarily done through homogenization, and we will talk about later in the course, where you basically bust the cells open to release all of their enzymes, proteins, and to a cell lysate or homogenate. You usually filter that or do another centrifugation to remove cell debris so that you have a liquid which contains the proteins primarily of interest or other intracellular materials. And if you have that lysate or you have the cell-free liquor, the next set of separations tend to rely on chemical separations, which take advantage of the chemical differences between your product and the byproducts that would be in the mixture that's being purified. These include solvent extraction, aqueous two-phase liquid extraction, absorption, precipitation, and ultrafiltration in this case would be another size separation. At that point, there's usually some sort of enrichment with chromatography. Chromatography could take advantage of the chemical differences between the products and byproducts or the functional differences. For example, affinity chromatography is also very popular for purifying proteins. And then at the end, there's usually final water removal to get to the right concentration, maybe crystallization, maybe precipitation. You may also do filtration, and you may have drying to end up with your final product. Through all these different steps, downstream recovery uses primarily three types of separations. So there's physical or size-based separations, and these include your filtration. Filtration, microfiltration, and ultrafiltration are all pretty much the same thing, just the difference would be the size that you're filtering. Centrifugation, which also separates things based off size, and then size exclusion chromatography, which is chromatography that separates based off size. You have chemical-based separations, and those could include solvent extraction, aqueous two-phase separations, which is basically an extraction with an aqueous solvent in quotation marks, precipitation, absorption, and other chromatography. And then you also have, in the case of proteins primarily, you have functional or affinity separation, so think of an affinity chromatography. Downstream is really expensive, so greater than 80% of the manufacturing costs of any bioprocess can be the downstream recovery. So to reduce the cost, you want to minimize the number of steps. Or if there are multiple conversions that can be done in the cell, to do more of those in the cell as much as possible to avoid downstream recovery steps, that's also ideal. So better strains, better biocatalysts. So titer has a really large impact on costs, especially for high value products like proteins, amino acids, vitamins, things like that. So what you're seeing here on the left plot is a selling price in US dollars per kilogram and the concentration in the starting material. So basically the higher the titer, the lower the selling cost or selling price, excuse me. And so, for example, things like ethanol, which we use for fuel, that's fermented by yeast, citric acid, monosodium glutamate, antibiotics, penicillin, cephalosporin are on the higher titers and the lower selling prices. And then some of these enzymes that are used for both clinical use as well as for industrial use, insulin, factor 8, urokinase, for example, are on the higher selling price and have the lower titers. And this impact of titer versus selling price is really a function of the fact that at the end of the day you have to get a concentrated product out. So there's more downstream recovery required if you start with a very dilute stream and you have to purify and concentrate it. Partly because you're concentrating, but also partly because if it's a dilute stream, there's more byproducts in relationship to your product, right? The higher the titer is, the more product to byproducts there are. This is primarily due to this cost difference is primarily due to the large downstream recovery costs for higher value products. There are three primary summary downstream recovery metrics that you need to worry about. So all the different types of chemistry aside, there are really three things that drive your downstream process. These three metrics that say how good your process is. One is delta, it's the concentration factor. One is alpha, the separation factor, and then the yield. Right. So the delta or concentration factor is basically at each step in the process, it's the final product concentration over the initial product concentration. So for example, you could have an initial product concentration, which would be the product concentration in the fermentation broth, and you would have the final concentration after, for example, a centrifugation step that would give you the concentration factor or delta. The alpha or separation factor is pretty much the same thing, except it's considering a particular contaminant. So it's the ratio of the final product concentration to the final contaminant concentration over the initial product concentration over the initial contaminant concentration, right? So this is the ratio of product to contaminant at the end of the process over the ratio of the product to contaminant at the beginning of the process. And this would be specific for each contaminant that's important. So each byproduct would have its own alpha. So for example, you may find one particular step in your downstream process or one unit operation, which is a step in a downstream process, is designed to have a high alpha for a particular type of contaminant, maybe a contaminant that's has a chemical difference from your product. And the last metric is the percent yield. It's basically how much of the product did you get out of the downstream over how much did you put in, right? So obviously if you have a very pure product but you lose 99% of it, that's not good, right? So you'd like to be able to keep most of the product as well. So the delta, the concentration factor, the alpha, the separation factor, and percent yield apply not only to the entire process, but can be applied to each unit operation or step to help identify steps for further optimization, right? So for you have the whole downstream, you can have a delta, alpha, and percent yield, but you also have a delta, alpha, or percent yield for each step, right? And it's easy to estimate based off the steps what your overall process is going to look like. So if you have several steps in your process, maybe one's a centrifugation, step 1, maybe 2 is a chromatography, step 2, maybe 3 is a filtration, step 3, maybe 4 is a precipitation, for example. For each of these steps, you would have a delta or concentration factor, and the delta of the overall process would be the multiplication of all of the delta factors for each individual step, right? Which makes sense. The same thing would be true for the alpha of the process, right? So again, the alpha is specific to a particular contaminant. So each contaminant would get a different alpha. But the alpha of the processes, again, is the multiplicative product of the alpha for each individual unit operation or step. And the same thing goes for the yield. So the yield of the overall process is equal to the yield of step 1 times the yield of step 2 times the yield of step 3 times the yield of step 4. Right? And this allows you to really be pretty careful and thoughtful in your design of a downstream purification. You can model each type of unit operation or step, and you can predict from the chemistry and the biochemistry what the alpha, delta, and percent yield should be. And so when designing your entire process, it's pretty easy to estimate what the entire overall process should be able to deliver in terms of percent yield, the alpha, and the delta. So with that, we will move on to the next set of slides to talk about some of the particular unit operations that we'd be using in our downstream processes.